Hi, this is Bill Foote, and we are in Stats 1, Lecture 6. And we're going to do the first half of Part 2. Part 2 is typically where we attempt to implement what we did in the lecture in a spreadsheet. We have the concept down, and what you see in front of you is a spreadsheet. Okay, this is a spreadsheet that we derived in Lecture 5. The Gaussian robots kind of go crazy now because they have been programmed into 11 intervals or 11 different, here we are, 11 different versions of performance. They're doing the same thing, GPA performance. We have 2 bits of data over here, a 2.0 and a 3.5, kind of at the end of the spectrum, each one of those. Again, the insight of this particular analysis is that we can have multiple environments. It is a 2-parameter mu and sigma hypothesis. So we can have one that is relatively low uncertainty for performance, and the other that is double it, much higher. And as we saw with the 5 and 5 or 10, here we have instead of 5, we're using 11, like the odd number. We now have 22 separate pairs of mu and sigma hypotheses. And because we have 22, the probability of any one of these, the uninformed probability, ends up being about 5%, 4.5% or so, I believe, 1/22. So over here we have the standing data for creating the grid. We're not creating much of a grid here with sigma. It's only 2 of them. We go through all of this rigmarole. Here's the normal distribution, the Gaussian distribution, 1 over sigma square root of 2 pi times e to the minus 1/2 z squared, where z is taking each of the data points, 2 for example, centering it, subtracting from it a hypothesized mean, and then taking that deviation and dividing it by sigma, a scaling factor. So z really reports the number of standard deviations that a particular grade point is from the hypothesized mean. That's what the z really is. And we're going to be using that again and again and again from here on out. But anyways, we know how to do this. We have a both and proposition here. Both the hypothesis and data point 2 GPA and another data point 3.5 GPA are all seen together. That's a likelihood times the probability that you even see the hypothesis, and we just put that all together in a product. Now, in more advanced courses and with a lot more data, we use a logarithm to do all of this, okay? Partly because of the overflow and underflow numerical issues inside of any computer. There's no such thing as infinity. There's some really, really, really small numbers, yeah, and some really, really, really big numbers, yes, but there is a limit, okay, as to what the math coprocessors that are embedded inside of our software, our hardware actually can manage. And also we may have limits inside of Excel as to what it is willing to take as a really, really small number, a really, really big number. So there may be software limitations as well. In any case, we find these joint probabilities, is what all of these are, and we normalize them. We sum them up. Okay, so the sum actually tells us the probability of all of the data across all of the hypotheses, even all of these, all 22 hypotheses, which are either or expressions, and either or expressions require us to add the probabilities up. So take this probability plus this one, plus this one, plus this one, all the way down to the bottom. And we now have the total probability of seeing the data D. Okay. Now that sum, okay, we take each of these and divide by that sum 0.03, and we get the probability of a hypothesis given the data. And here we have another problem though. We have two panels of information about hypotheses buried inside of a plausibility number. And to handle that, what did we do? We made an associative table. We associated all of the mu's with all of the sigmas. We have only 2 sigmas. That's real easy. But we have 11 mu's this time instead of 5. We could make 51 of these mu's, and we could have far more sigmas. And Excel could handle that quite easily, actually. Now we're only going from 1 to 4 in any case, because that's the context of grade point averages. Really, they probably go from 0, but we're not going to flunk anybody today. So now we have these. We have for each of these mu's a sigma. Oh, we have 2 sigmas and another sigma. We have 2 probabilities, and these are mutually exclusive, completely exhaustive probabilities. So what do? Either or, we add them up, and we get a distribution of mu's. Now, if we sum up this distribution, guess what? Well, it should make sense that it's this way. These have to all add up to 1. Well, they naturally add up to 1 because they're basically adding up all of these, which add up to 1. You can see that down below here. Put the cursor down for you. Down here in the sum. Okay. So it's all everything about everything. So these are true probabilities. And one of the first things I want to do with this is just make a little heat map, so it's a little bit easier to see. We have something called a data bar that we could use. And let's just illustrate it. Select all of these mu's. This is the probability of mu, all by itself, by the way. Okay, it is conditioned on the data. Okay, we'll give it that, the data. But it's across all of the sigmas. The sigmas, the math people will love this among you. The sigmas have been integrated out. Cool. All right, very cool. And we're just left with mu's. Mu has 2 experiences, a low sigma and a high sigma. And we have 11 of these. So how can we depict this? We can use conditional formatting and a lovely little invention called a data bar. Let's use blue. There we go. And doesn't that look like a nice little histogram? And that is, it's a lovely histogram. It's exactly what we would want to use. Now, we can't make histograms on a row like this, but there is another little thing that they offer us, a rating scale. Let's just try it. I don't particularly care for it, but it's better than nothing, I guess. So we have data bars, color scales, icon sets. Let's use icon sets. So these are all pretty good, but I want to use this right here. So that's low, that's high. I don't know. You could put colors here. You could do whatever you want. Now, the other thing that people do, which I've had many colleagues not like this ever, make a heat map. So this segment, Lecture 6, Part 2A, we're going to call Gaussian heat, just to turn it up a notch. And going to conditional expectations, We can go to color scales and put all sorts of things in there. Now, this is a real traditional heat map. Red is bad, green is good, and something in between. Okay. Got oranges and green and lighter green, and so on. Okay, and pretty obviously we see that the spread of the higher volatility performance environment allows for much wider, much more dispersed. That's what sigma really is looking at: dispersion of plausibilities, where the lower level of 0.5, the lower level of performance uncertainty, is much more concentrated, as you can see here. Okay. So that's something you can do, you can play with. All right, so that's kind of interesting, but what we're really trying to do is ask the question, what can we expect? What is the expectation of a mu, of a score in this system? And that's a weighted average. Each one of these plausibilities contributes to a level of mu. And this is one interpretation of that. Now let's just do that. That's pretty easy to do. We simply need, rid of this guy, we simply need to do the product of PR mu times mu. Okay. So this gives the contribution. Here's PR mu times mu. Very low contribution. And just copy this all the way down. Okay. Much higher contributions in the middle. Let's make these numbers a little bit easier to see. Okay. And now what we need to do is add them up. Use sum to do the adding. And let's give that 2.73 is the average in this system, given all of the assumptions, including numerical assumptions. Big numerical assumption is 10 intervals, 11 nodes for mu. Twice over makes it 22 pairs of mu and sigma, and only 2 for the sigmas. Okay, so that's a major assumption that has to be called out immediately. 2.73 is our average. And are we near that average or not? We're far away at 3.5. We're far away at 2. And a 275 isn't too shabby a score. Perhaps we want to do better. Okay, so that's the story of the expected value. Now, there's another story that we can say. What would be, okay, the average greater than 3? Greater than 3 in our story here. What would be the average greater than 3? Greater than 3 would only cover these possibilities. Greater than 3. We could interpolate between 2.8 and 3.1. We're not going to do that. We're going to make a rule and say anything greater than 3 is covering the events, the potential hypothetical events of 3.1, 3.4, 3.7, and 4 rho. Okay, so that means we're only going to be using these at all. So let me write that over here. Here's the greater than 3 group. Here's one potential outcome. And there are the others. Okay, these are GPA greater than, put that up here. Okay. And now their raw probabilities. So we're gonna pull up the raw probabilities. Let me just bring them over. They're going to be this one. There we go. So we can see these are they're not very plausible. But can we still get a weighted average out of this? Well, in the current form, we may not. We may not get a weighted average out of this. We have the same problem here. These do not add up to 1. So within the context of GPA greater than 3, they don't talk about the total set of outcomes, events called 3.1, 3.4 through 4. They have to add up to 1 to do that. That's the rule of probability. And that's also the rule of weighted averages and probabilities as weighted averages. So over here, we had everybody on board from the smallest to the largest. And all of those probabilities, of course, added up to 1. Okay, that's wonderful. That's cool, whatever you want to call it. So what we're going to do here is we're going to add these up as well and normalize them again. So this is something, again, that we know how to do. We did it over here. We took all of these, which when you add them up, don't add up to 1. They can't. They're not designed to. They're all either or situations, but they can't add up to 1. We have to normalize them in order to have an intelligent discussion about which one's bigger than the other one, okay? From the point of view now of forming expectations, we need probabilities. So we're doing very much the same thing over here. Okay. And what do we do? So we now do the probability of any of these mu's greater than 3 in this unconditional sense. That will be equal to this, which will get the biggest score divided by that normalizing number. And now you see, relatively speaking, the 16 is 42% that whole group. And the 9.98%, 9.98% is 20. There we go. 28% of the whole. And this is 15%, and that's 7. Now you can see that these add up to 1. They should. Yep. Okay, we did our arithmetic correctly. And now we take these numbers and multiply them times those numbers. We're taking these and multiplying them times these. That will be our weighted average. Take the probability times the outcome, 0.449, almost 1.5. And these are the grade point contributions to the average or the expected value of grade point in this subset, subspace, I like space better, subspace of all of the mu's that we had considered. And of course, we're going to add this up. Let's just borrow this sum over here. It's 3.34. 6/8. Okay. So kind of an interesting exercise. I'll take a almost a 3-3-5 over a 2-7-3 any day. Okay, so what do I have to do? I have to up my game in performance. And if this was a W-2 job in the United States, taxable, or even a 1099 job, from a tax point of view, I'd be getting money in my checking account, right? I would love to get a bonus. And that's reasonable. Why? Because that's more money. I can give it to my family. We can grow. Maybe can take some relaxation together in an extended vacation. Everybody's happier and rested, and the family is happy. The family's happy. I'm certainly happy. And it's important that the family be happy and stable and grow, because we have enough going on in the universe to interrupt that. So yeah, I'm going to perform better. There we go. There's always another reason why we want to do things other than simply make money. We're doing it for a reason. That's pretty important here too. But this analysis can help me do that. Okay, so we just did 3 things. We use an 11-point mu system here, 10 intervals. We did this across two different performance environments, a low uncertainty and a high uncertainty environment. We postulated that each of these 22 hypotheses, 11 times 2, are equally likely. We sampled 2 data points, 2 and a 3.5 level of performance, use the Gaussian distribution to try to understand the relationship between data and hypotheses, what's in our mind and what's outside of our mind in front of us. That piece of paper is definitely outside of me. Now I helped produce it, yeah, that too, and I helped produce that 3.5. But in my mind's eye, I would like to, of course, do better. I create joint probabilities, add them all up. The probability of seeing those 2 data points at all is 3.27% in the context of all of these hypotheses. I then normalize these joint probabilities using that sum, and I come up with the probability of any one of these hypotheses given the data. And the hypothesis, remember, is a pair. It's a pair. It's a mu, not an apple. It's a mu and a sigma, and they're all mutually exclusive and completely exhaustive of all the range of things that we're considering. We organize this into an associative table. What analysts do all day, all night is build tables like this. And we try to visualize it as well. So we realize that this mu can happen in one of 2 mutually exclusive ways. We add up the probabilities. We do so for all 11 of those. And we do the same for the probability of sigma. Definitely, this model is favoring a high volatility environment. Why? Because there's a lot of move, a lot of scale going on here between 2 and 3.5. What if this was closer to 3? Watch things change. Flips right around. Look at that flip. Look at that flip. It's now 60-40. Okay. So you play with this. A lot to play with, but there are some things you can play with it. And then we visualized each one of these with something called a conditional formatting up here, a data bar. Okay. And we did something which a lot of people would say, that's very misleading. Not to me. It looks like the heat map looks like it's cold in the middle and really hot in the end. Okay, that's one way of looking at this. Temperature distribution inside our slab here, which is actually what we're solving for. We're actually solving for the temperature distribution of a uniform slab of metal. Thermodynamics engineers will love this. Okay, called Laplace's equation. No more, no more. Okay, and then we also have a rating system here because we can't build little data bars down here. They won't let us do it. Call Bill Gates. Tell him to put the arm on those folks. And then the third, the second thing we did was we calculated an overall expectation of grade point average. Okay, given that these are the potential outcomes, okay, our grid, and these are the plausibilities of each of those outcomes, the probability that a mu will occur across all the sigmas. And we then multiplied the probability as a weight times each outcome. Each outcome comes in at a plausibility level or a weight. And it's a weight that, and the sum of the weight add up to 1, just like because of probabilities. Okay, cool. So these are all individual contributions of each of these mu's to the overall 2.75 in the middle. 2.73. So it's just shy of this number, 2.80. It's somewhere in between 2.5 and 2.8. Well, that was not enough to do. The last thing we did was we created a subspace of our outcomes, GPA greater than 3. I know it's just a line, it's pretty easy. Sets, yeah, I like subspaces. And we ported over the outcomes here, but we also ported over the raw plausibilities of each one of these. And of course, this can't be a weighted average, because if 3.1 through 4.0 is everything we're considering, it's a new universe here, if you will. Completely exhaustive, mutually exclusive set of outcomes, then 16, 9, 5, and 2 isn't going to cut it. We have to normalize these, like we did over here in L, normalize these by summing these up. That is literally the ogive probability, 34% of all of those outcomes are going to be greater than 3 and less than or equal to 4. 34%, which means anything underneath this is going to be what? 1 minus 3485. Okay, you can figure out what that is. 30, 63, 15, pretty close. Okay, and here's the normalization. 48, 28, 15, and 7 will add up to 1. And again, we do the normalized probabilities times the outcomes. This is the contribution of the lowest outcome. It's the contribution of the highest outcome. And now we get a 3.34. And of course, we much rather would have that level over 2.73. So our job is to game, get us over the 3 hump, okay, into the 3 to 4 range. Of course that is. But that's, given everything so far, that's what we would expect. Okay, I'll leave you with that. Colorful display and some new techniques, and using exactly the same models that we have before, this time forming expectations. Thank you very much for your kind attention, and we'll see you in part 2 of lecture 6. The second half, and that's where we're going to do outlier analysis.